A great pleasure to introduce our first speaker, Dr. Roberto dos Reis, here at Northwestern University. He is a research assistant professor, and he specializes in the development and application of advanced methods for characterization using TEM. So without further ado, I'll pass it over to Roberto.
Let's see, can you see my full screen?
Yes, we can.
Perfect. All right, thank you very much all. Welcome back. Thank you, Teresa, for the kind introduction. So I'm Roberto. I'm here at Northwestern MSc and the Nuance Center. So what I'm trying to do here in the next 30 minutes is just give a brief overview of using like diffraction methods to explore the reciprocal space, right? Similarly of what Teresa did in the morning, I want to try to explain like the basics of it, but of course, like not also like introducing like a new developed and introduce add nuance as well. So with that, let's see. There we go. So I divided this talk in like three. Yeah, no, that's fine. It happened. I divided this talk in like three portions. One about the basics of the reciprocal space, right? And what you can get from that, and basically what are the differences that you can get, right? What are the informations that you can get from that, and a little bit about the acquisition and different modes, and a brief introduction about applications. So I'm going to leave most of it for the speakers after me, so they have like great results to share with you. So with that, let me start. So it was funny this morning seeing Mike showing this, the tetrahedron of material science, and I was laughing when I saw that. And yesterday night was preparing this talk, and then what's the best way to kind of like summarize what I want to say here? And this is a great picture. Actually, there are so many versions of that online that I kind of like. I actually don't know what's the original one, so I'm sorry about that. But yeah, so basically what I wanted to show here is that all this, the relation, right, between the structure and properties, it is very important, and like especially like to probe like the performance of material, like regardless of the material, right? So that in that many different ways to characterize that, and we saw like this morning like these beautiful talks about the EBSD, like a TKD, and different like different scales too, right? And really depends what you want to achieve in terms of material design and application, right? Well, what I want to focus on here is this like characteristics of TM, of course, city, and a crystal may be like generated by repeating a certain unit of pattern to like translation of a certain lattice called that we call like real lattice, like the direct lattice. So as you can see here, this is a simple diagram of that. And on the other hand, like the basic tool to study like crystals is the diffraction pattern, at least in my opinion. Is a diffraction regardless of the wavelength. So it's like a wave you can it is also applicable to like X-rays, for example, right? So you have a diffraction wave with the wavelength that is a similar order of magnitude, and then the operation between the transforms like the direct space into associate space, the reciprocal space is that what you want to observe through analyzing like diffraction spots, right? So historically, like the reciprocal space was mentioned back in like the 1850 by this was like very early, like before like any introduction of any actually microscopes. So that was like in the 30s, 1930s, and then was like reshaped. I put here like rediscovered, but it's like sort of like a reshaper and reformulated by Ewald and Law. Ewald is that the same one from Ewald sphere, yes. And then they stated that for any family of lattice planes separated by this distance d here. So there are like reciprocal lattice vectors that are perpendicular to the planes, as we know as a G vector, right? So back on the methods that have high spatial resolution and precision and chemical sensitivity, right? Those are the two main points here that I want to emphasize throughout this presentation. The basics, right? What's the fundamental of the scattering? So and this is from Willis and Carter, like a TM book. So most of you might be familiar with that. So assuming that you have like a uniform intensity, any sort of wave here, actually, it could be like X-rays here, but more specifically on using electrons, right? So after passing your sample, you have basically like two variations that your sample basically perturbs your wave in different ways. So one is that varying the intensity, and the second one is the directions of that electron wave. So that will give you like the points in the reciprocal space, and this will give you like your intensity basically, right? And then the two fundamental pieces that you should know if you want to analyze any diffraction pattern, regardless if it's amorphous or crystalline, is that the atomic scattering factor here. So the F, which is the atomic scattering factor here, is that is a measure of the amplitude of electron waves scattered from one isolated atom, right? So this is like independent if you have like a collection of atoms or not. If you have one atom in a vacuum and then you shoot an electron in there, that's why that's basically like the equations that dominates that. And that one thing that I want to point out here is that the dependency on the Z, right? And the amplitude is the module of the scattering factor is proportional to the intensity that you're going to see in your screen, right? And this is a nice summary for like different Z values here, like from aluminum to gold. And then this plots basically like the equation. And this is something good to keep in mind, that dependency on Z, you're going to show up later also in this talk. And then you're going to show up in your experimental experiment too, right? That and then I have had like many questions about that. How can you distinguish like different atomic species in your sample using diffraction, right? Then using your basically like the amplitude of your diffraction pattern. So the other portion that's a little bit more related to the idea of having actually a periodicity in like a lattice, a periodic lattice here. So, and then you're gonna see here the introduction of the HKL indexes. It's like the Miller indexes here, and the position, the atomic planes that refers to the atomic planes of your sample, of your crystal, and the position of the atom in the cell given by like the X, Y, Z here. So if you integrate everything for a unit cell, right? So you have that relationship of intensity of that specific, the diffraction related to that unit cell to the structure factor, right? And that's very important. It's going to be important for techniques such like conversion beam electron diffraction that we're going to tackle later, and also important for like micro-ED that you're going to see this afternoon, right? So how are you going to retrieve your the position of the atoms in the like a crystalline lattice. Just a quick example here that you might be familiar with, just to show how important that concept is, right? This is an example for like BCC lattice. So if you expand that equation, right, giving the positions, the atomic positions in your BCC lattice here, you're gonna find out that you have like an amplitude equals 0 if you have HKL mixed like even or an odd positions, right? So you're gonna have points that you have completely destructive interference which at the end of the day, that will form like a diffraction pattern and your so-called kinematically forbidden reflections. So a typical example here that you might be familiar with is that like silicon example that some of diffraction points appears in your diffraction pattern that due to like double diffraction within the specimen, right? So that's why we call here like kinematically forbidding, assuming that everything is perfect. So you have this forbidden reflections that might show up due to like dynamic reflection or like double diffraction, etc. Even like double diffraction in defects, for example. Continue on. So now that you know like all the basics, then you'll be able to solve complex patterns like this, right? And then I really like to show this like every talk that I give on diffraction, because this is one of the first, if not the first, transmitted diffraction pattern that was back in the 30s. This was like collected like a low voltage, actually like a 45 kV, I believe, and that was a mica sample. And this was one that was collected in the prototype that would be called later TM, right? The TM actually came up in the same, like a year after, 2 years after this, the same year basically, yeah, for a different group. But that was like collecting a prototype, and then basically it includes all the basics of diffraction here, right? So you have like a lot of the Kikuchi lines that we saw this morning. You have like dynamic diffraction, you have like the positions of the diffraction patterns, etc. That is very complex. So it's a very complex experimental result, like that you wanted to go back and analyze point by point. So to get to that, right? So you have to decide how you want to collect a diffraction pattern, and this is like basically falls into depends on the material that you want to analyze, and depends what kind of information that you want. So you might want to collect in this configuration that we call like parallel beam, right? Which is like so-called like select area diffraction, that you basically introduce a select area aperture and produce a diffraction pattern, right? So that is typically what you learn when you take like the classes that are like introductory on TM, right? And it's really simple to collect, right? So you put an aperture and then leave with your diffraction pattern that is easy to index. But it's a little bit limited in my view, and then some other folks can talk more about that too. That you have a limitation, like spatial limitation, right? So you are limited by you collected this information from a certain area that is limited by your aperture, right? So you have a certain size of aperture that you basically cover one portion of your sample and then collect that. And then the other way to collect that more precisely, I would say, is that by changing that conversion angle, where you can really like expand the type of information that you can acquire using electron diffraction, right? So this is like three characteristic diffraction patterns. There are within the conversion being electron diffraction mode, right, where you converge the beam on your sample, and by tuning that semi-angle aperture or angle or alpha here, you can produce a different, generate a different sort of pattern here, like that give you like, that helps you to emphasize different information from the sample, right? So another way, and that has been shown like for decades now, that are very useful for different applications. So I'm going to go over a few of them now. So like, for example, they're very susceptible to like thickness determination, to the thickness of the sample, right? So this is a nice example that I always show, is that you see those features inside the disk when the sample when you analyze like thicker portions of the sample, right? So things like, for example, strain measurements, right? So that you can use that other technique that is large angle, that is so-called large angle conversion beam electron diffraction. So you can analyze those Kikuchi lines similarly to TKD actually, but more like on more localized, I would say. And analyze like measure like strain, for example. Other things such as point group determination, like local symmetry on very very localized to like nanometer resolution here. And also like phonon dispersion, for example, like information about the vibration of the atoms here. So typically, there are different ways to collect a CBAD, right? Conversion beam electron diffraction. So one thing that got more popular recently is that also with the increased accessibility to like STEM machines, like scanning transmission electron microscopes, it become more feasible, I would say, to collect those patterns using in STEM mode, right? So what is STEM for that matter, right? So the STEM, basically what you do is just you converge, you have a probe forming aperture. So you define your aperture that defines also your angle that I mentioned earlier, your alpha, right? And then you converge that, form that probe, converge, and then you obtain your diffraction pattern at your detector, right? If you don't have any sample in there, so you're just gonna see a disk, basically. So that the way you acquire the images usually is using like annular dark field detector, annular bright field detector, etc. And that is the like the basics of STEM. So now when you insert the specimen, so you have your diffraction pattern at the end, but till like a couple of years ago, we are basically like throwing away all the information from the diffraction pattern. So you were basically just collecting images. So folks realized that why not start collecting this to obtain all this rich information that is contained in this diffraction pattern to probe like different properties of the material, right? Not only leave your microscope session with diffraction, an image here, but also collecting diffraction pattern. And I'll say over like 5 years ago, a little bit more, so the introduction of like direct electron detectors really helped on that, because they, what I call here high-speed pixelated direct detectors, they help you to collect that at the same time that you collect your image, right? Because they, especially because they can match the speed of your imaging collection in STEM mode. Right, so now you have like different capabilities for that, and this is the technique that you might be familiar with or might have heard. It's called like 4D STEM, when you measure your two-dimensional image together with your two-dimensional diffraction pattern. So here, Northwestern, we've been using that in the last few years. So, and even expand that to like call like ND STEM. So not limited to 4 dimensions, but like adding other dimensions to that. So as I mentioned before, so you have X and Y on the real space here, and then you have your QX, QY on, oops, sorry, gonna go back. QX and QY on reciprocal space. And that you collect like basically a diffraction pattern at every pixel here at the speed that your detector allows you to, usually like in the microsecond range for 4D STEM. So, and then as I mentioned, you can definitely expand that to like other dimensions, such by tuning that convergence angle and then tuning your camera length on your microscope to collect information from your like 3rd dimension here, what I call here QZ, right? So by collecting patterns that contain like high order Laue zones here. And then if you expand even further, you can expand by dimensions by adding like external stimuli, for example, like in situ processes with using like this ND stem, like for example, like heat, pressure, bias, and light. And there are like many different vendors that manufacture this this different TM holders that allow you to collect this type of data. And then you can, of course, add time to this, and then you have the whole package of ND stem here. So one thing that was very important here, and I mentioned in the previous slide, was like how important are these detectors and actually the expansion of this this technique, and also like the introduction of this technique like a few years ago. And then here's like a nice summary. This is actually from Gatien that we speak after me here, that just to show like a couple of the detectors, right, and the frame rate they can achieve. Another thing that is very important here is their ability to detect the electrons at different voltages too, when you operate the microscope at different acceleration voltages here. So the good news here for us and for our users is that they're all available, new ones. So we can, you have like from the real camera that was like recently installed in our GL 2100F to like the newest like stellar camera that was is installed in your 300F here. So if you have more questions on this, you can definitely reach out to us, to our facility managers, Paul Smith and Zhao Binghu. And feel free to ask questions, and we can definitely help you on finding the best match for your material here and what type of analysis that you want to do, right? So one thing that I always like to point out here, so yeah, so we have the ability to collect that large amount of data here, right? So, and this is a nice summary that was published like last year, so showing like a different cameras. So some of you might not even have worked with this, like there was like the old days of microscopy that you used to collecting films and then you have to reveal them later. So that was, we basically like had to collect like one by one, right? So one diffraction at a time and then reveal that to obtain your result. So now with the advances in detection, right, so really increase the amount of data that you collect, and this is create another problem, right? Which how are we gonna analyze such a large amount of data? And then Northwestern and then Nuance Center has been working on like creating like a completely introduced, I would say it's better, a new way to analyze those large data sets. So just stay tuned. You're gonna introduce that pretty soon. And this has become like a really big problem, like I mentioned. And then most of the users that I work with or collaborators, that's the main bottleneck for analysis and even for usage of these new techniques. And what ends up happening is that people fall in the comfort zone that you're just going to collect one diffraction pattern and goes back basically like without like utilizing all this like potential like new techniques that will unlock like different results, different type of information from your material that you're analyzing, right? So I want to use also this opportunity to encourage people just to try it out and then really use that, which is much better today than it was like say 4 or 5 years ago in terms of like data analysis. In terms of applications, right? So like I mentioned in the beginning, I'm going to leave more to the speakers, but I was putting together this panel yesterday, and then that does like all great examples for that using like diffraction, not only diffraction itself, but also this scanning diffraction like 4D and the stem here. So you have the ability of to correlate, right, like your diffraction pattern to your reciprocal space to your real space through these techniques, right? So here and collect different properties from your material. Like for example, here you have like nice strain maps. Here you have like phase analysis of different grains. even like more complex techniques such like dichography to retrieve the phase of your object here. In this case, it's like a moly disulfide 2D material. Other like techniques that you can play with. So for example, using like Moire patterns that you can distinguish like different grains in your material. Like strain analysis again on a very like localized in the nanoparticle, right? To like microED when you can basically like map out your like 3-dimensional like reciprocal space to that. So, and that's a good segue for my next slide, which this is the set of speakers that we have after me. So they are great. They're going to speak more about like the results. And we're very glad that they all accepted our invitation. And then with that, I can pass on back to Tirza. If you have any questions, so please put it in the chat. I can address later.
Thank you so much, Roberto. We'll just wait a few seconds here to see if any questions pop up, but like Roberto said.
Question, Roberto, Vinayak here. Hey, dynamic range, can you tell us if this pixelated detector, especially when you have higher order Lave zone at 0, there's a large intensity difference. So maybe if you and or Anna could make some comment, that would be great.
Yeah, definitely. This is a good point. So especially when you wanted to get information from reciprocal space, right? So usually, I think most of you that are here in the audience perhaps have done or collected a diffraction pattern, right? So you usually use the center beam stopper, right? The beam stopper, so-called beam stopper, and basically use that, and then you might relate to that to be able to see other diffraction spots that are a little bit farther from the center spot, right? So, and that's basically because depending on the dynamic range of your detector, you may or may not be able to see the center spot together with the higher scattering angle spots, right? So the new detectors here, especially the stellar detector, it has like a great dynamic range. Yeah, I just saw a question here. It has a great dynamic range that you can use. It can collect the diffraction pattern without the beam stopper here. And why is that important, right? So Vinayak mentioned that especially when you want to collect like high order Laue zones for that ND stem 3D analysis, you do want to have the ability to have a good contrast from the center, from the 0 order Laue zone and the higher order, right? So that's one thing that has been really great on the new detectors. And then definitely like GTN is one of the manufacturers here. They really did like a great job like making that camera with a much better dynamic range. The other point here is that that I didn't have time to mention, but is this using a lower voltage, right? So you have access to a higher order Laue zones, right? So that also having detectors that can collect at lower, they can collect diffraction patterns when you operate the microscope at acceleration voltages that are lower than the typical ones, say like 60, 40 kV, like 40 to 60 range. That is not typical. That helps you on that. Of course, there's some limitations about the sample, but that's another issue, right? Yeah.
Thank you, Roberto. So we're gonna move along, but remember, if you have questions, please put them in the question and answers section of the Zoom, not in the chat. That way they can be answered later. So I would like to introduce Michael Martynowycz. He's a research scientist at the Hughes Medical Institute at UCLA, and he is here to talk to us about the cryoEM method for microED. So I'll hand it over to you, Michael.
All right, is this showing up correctly for everybody?
That looks great.
All right. So let me start off by just saying thank you again for inviting me to give this talk. I'm very excited and interested to hear everything going on with electron scattering. So yes, my name is Mike Martynowycz. I'm a scientist at the Hughes Medical Institute at UCLA. And I'm going to talk about something a little softer, much different than we've seen thus far. You can read the title of the talk, which is The cryoEM Method MicroED, a powerful tool for solving protein crystal structures. So what I'm talking about today is cryoEM, which is electron microscopy at cryogenic temperatures, so at liquid nitrogen temperatures or colder. And MicroED is an acronym for microcrystal electron diffraction. And you'll notice today we've heard a lot of people talk about structure and structures and crystals and things like this. And I thought I'd take a step back and kind of resettle everybody who might not be as familiar with what we do and why. Why were we talking about structures and what does that mean? We're talking about trying to figure out where all the atoms are in something, at any given time and in X, Y, and Z. And why are we doing this? So for me, for proteins, for biological materials and pharmaceuticals and things like this, we care about where all the atoms are, or the structure, because of a fundamental tenet in structural biology and really all structural science. And this is something that we refer to as the structure-function relationship. And this is basically the idea that if you can tell me where all the atoms are in something, I can figure out what it does. And if you look at this lovely slide here, this is about proteins. You can go to the protein data bank, and there are over 100,000 structures of proteins. And each one of these is a little machine in biology that performs one or multiple functions for an organism to survive and live. So for me, it's if I can figure out the structure of a protein, I can figure out why it's working properly or why it's not working properly and how to fix it or how to make a drug that might fix it. And that's where we all are right now. So in order for me to fix human disease, I need to figure out how a protein works or functions. And in order to figure out how a protein functions, I have to figure out where all the atoms are in that protein. So to give you an idea of this concept and why it works, we can go back to Fleming's search for the first antibiotic. And everybody can, in their head, say penicillin. And before penicillin was actually discovered, the first antibiotic that Fleming found was actually a molecule that you can find in your sweat and your tears called lysozyme. It actually is expressed by tons of species and found throughout nature. And what he found was that if he incubated bacteria with this protein, it didn't grow. So what we know now is that it does this by cleaving the cell wall on the outside of bacterial, gram-negative bacteria, which are bugs that make you sick. And it cleaves it at a very specific place. And we know this because we have three-dimensional structures of lysozyme that show us where this nagnam, this sugar on the outside of bacteria, binds in lysozyme and where it cuts it. And from this, we can figure out how to build better antibiotics. So this is an idea of why we do what we do and why it's important. So another thing I want to address here is, because I'm talking about proteins, and if you know anything about biochemistry, the first question you might ask is, when I'm talking about protein structures, is why are you talking about electrons? And why talk about electrons at all? So in structural biology, the go-to approach for any of this is to grow crystals of proteins, and you put them in an X-ray beam and do something called X-ray crystallography. And this is the go-to method for structural investigations, particularly in structural biology of proteins. So to do this, we have to grow like these giant protein crystals that we are showing here. Maybe I'll get this laser pointer going. These are huge crystals of protein that are grown by just kind of waiting and mixing stuff. The problem is we can only do this for big protein crystals. Most of the time, we don't grow these big, giant, beautiful crystals. You try and grow crystals and you get these tiny little micro and nano crystals that are just little tiny drops. And you can't even shoot X-rays at them because they're so small and they don't produce any signal. So we decided to go to electrons and use electron diffraction because electrons interact with matter orders of magnitude stronger than X-rays do. And on top of that, they deposit less energy, which means there's less radiation damage. So talking about what we do, this cryo-electron microscopy. So in cryoEM, we like to divide what we do in the microscope into two basic camps. And that's techniques where you take pictures, where you refocus the scattered electron beam back into an image, and diffraction-based methods, which like 4D STEM, you collect the scattering from the sample, whether it's a crystal or not. So of this, the big major techniques nowadays are two-dimensional electron crystallography and micro-ED, which is what we're talking about today, which is microcrystal electron diffraction. So it is very confusing to biological crystallographers to talk about electron crystallography because it has a very rich history. So the reason we just don't call it all electron crystallography is if you talk to people about this, they imagine electron crystallography of two-dimensional membrane proteins, because this is where this all started. And that's Henderson, who won the Nobel Prize for cryoEM, was looking at two-dimensional crystals of a membrane protein called bacteriorhodopsin. And it's in a native lipid bilayer, and it crystallizes by itself in 2 dimensions. So you don't have to grow crystals. It just will form on the sample. And what they did was they formed these this structure in 1975 by taking a picture, taking the Fourier transform of the picture, which would give you more or less a diffraction pattern or an optical diffraction pattern, and using the intensities or the amplitudes from the Fourier transformed image, along with the phases from the raw image, to get multiple projections of this two-dimensional protein crystal. There's this lovely wooden shaved tube here. What they found was that this membrane protein has these transmembrane helices that allow it to function. So they worked on this for like 15 years before they found out that they could push the resolution and see more than just those tubey blobs by, for every crystal they found, they'd take either an image or a diffraction pattern at multiple angles. So any given angle. So you have hundreds of crystals where each crystal is one diffraction pattern or one picture. And you would take the phases from the picture, and the diffraction pattern would give you the amplitudes. And you can combine them together to get higher resolution, and you can make a nicer model to about 3.5 angstroms. And people were doing this for two-dimensional crystals for about 15 more years again, until 2005, when Gonen and al. Showed that we could use molecular replacement rather than images for the phases. And if you just use the instrument in diffraction mode, you can actually push the resolution from 7 angstroms to 3.5 angstroms, and now to better than 2 angstroms. So truly into the atomic age where you can start seeing features of your protein. The angstrom resolution tells you approximately how well you can resolve different features in your map that you get. So micro-ED is different than electron crystallography. So it is the TEM and diffraction mode. We are going to use 3-dimensional crystals instead of 2-dimensional crystals. The data collection is entirely different than what I've described. Sample prep is different, and the data analysis is entirely different as well. So this is why our lab renamed this a new thing, micro-ED, in 2013 when it was first described. And to give you an idea of exactly how this might look like in your head, because this is just all pictures and talk, I have a lovely video of what a standard micro-ED experiment for any kind of crystal would look like. And so you could imagine you have a TEM sample grid where you have deposited a slurry in liquid of small crystal samples of protein or small molecules or something. And we plunge freeze this into liquid ethane to vitrify the crystals in place. This means that we freeze it so fast that crystal and ice cannot form. We insert this into a transmission electron microscope and identify a single microcrystal. That microcrystal we rotate in a parallel electron beam and collect the diffraction data as a movie on a fast camera. So that's what we're seeing here. So you could imagine that after this is done, you can look at all of the individual frames on that movie and map out where all the spots are and how strong the spots are. So, and where the spots ought to be. So you can, this is called indexing, to figure out what your unit cell is and what the amplitudes of that unit cell are essentially the square root of these intensities that you've mapped out. So you do this for every frame, and you can map that into a three-dimensional, it's called reciprocal space, where you have all of these amplitudes and all of the indices. So we take all of those and combine them with the crystallographic phases to give us a map. A Fourier transform will give us a map. And into that map, we build an all-atomic model. So that data that I just showed you gave us a 1.7 angstrom structure of an enzyme that breaks up other proteins called proteinase K. So this entire protein was solved in a transmission electron microscope at 100 Kelvin using one sweep of data that I just showed you in approximately 60 degrees. And it was done using a total exposure in the microscope of only about 1 electron per angstrom squared. This corresponds to between 2 and 4 megagrays, depending on the accelerating voltage you've used. You can see that all of our atomic model of that protein fits into that map here on the left very well. And when we use these types of exposures, we can look at things like disulfide bonds, and they're not broken. They haven't broken apart. They're still intact. And we can even see that negatively charged residues are still occupied and haven't been damaged. So using this specific approach, we've been able to solve many things. And just to show this to you a little more clearly, these experiments are conducted on standard transmission electron microscopy grids, or TEM grids. You can use lacy or hole-spaced carbon. You can imagine those little holes here in the carbon are, about a micron, 2 microns, very, very small. This is what it looks like when we prepare these samples, where we add some crystalline slurry. We blot away the extra material, and yeah, we just drop it, like plunge very quickly into ethane to freeze that. So in this method, we've done many crystals, and when the crystals are too large or imperfect or ugly, in the past, we have been able to just sonicate those crystals, meaning just put them in like a jewelry washing machine, and it will break the crystals up into tiny pieces that we can use in the transmission electron microscope. There are some examples of this here. As I've said earlier, so this is a new technique. Our lab put this out in 2013, and it's been growing ever since in terms of new structures. We had a big breakthrough in 2018 where we showed you could do this for nanocrystals of materials like metals and salts and all of this, natural products, pharmaceuticals, anything that's really, really tiny that might not want to grow a big crystal. For us, as a lab that is interested in protein structure and function, our big target are things called membrane proteins. So this one down here on the corner is an example of that. The ones we care about are membrane proteins, because this is what all the pharmaceutical drugs that we're making nowadays are targeting. We make drugs that target membrane proteins to try and treat diseases, because membrane proteins kind of are gatekeepers of the cell, and they tell your cell like, hey, start making that, stop making that, all kinds of stuff like this. This membrane protein was solved by my colleague Xian Liu in 2018, and it's a non-selective cation channel called NAC. And when he went to go do this experiment, he made these crystalline drops where you mixed protein and salt and you hope it forms crystals, and they looked something like this, which is, if you're a crystallographer, it looks like garbage and it doesn't look like crystals. But when we put that on a TEM grid without sonicating it, we saw these beautiful little tiny cubed crystals. And when we collected diffraction from them, we were able to determine the crystal structure to 2.5 angstrom resolution and actually catch a new state of the protein, which is very exciting. So from here, what we did is we wanted to say, okay, well, now that we know it works for membrane proteins, let's move on and see if we can do this for membrane proteins that are really important to human health. And as a brief, just very small introduction to that, these are called G protein coupled receptors. something like half the drugs to 70% of the drugs, depending on which review you read or who you ask, are developed for these proteins. And they're very, very similar proteins in the human proteome. There's about 700 different ones. They have 7 transmembrane helices, just like that one from Henderson, Bacteriorhodopsin. They sit on a membrane like this. And the whole idea with what these proteins do, you can imagine that this is a protein sitting in a membrane. You will become accustomed to my horrible PowerPoint art. Things on the outside of the cell, agonists or antagonists, you don't have to know what that means. They can come and bind to the GPCR, and they cause a cascade of signaling to happen inside of the cell that ultimately results in adenosine monophosphate or calcium to be effluxed or created in the cell. It can trigger some kind of hormone production, or it can trigger the internalization of that receptor saying that it's broken, or we want to reduce the sensitivity to certain things. So these receptors can't be imaged very easily because they're very small. So that receptor, before it comes and binds these other things and causes this cascade, is only about 30 kilodaltons, so very, very small membrane protein. The only way we can solve these membrane proteins and get them into crystals in order to collect diffraction from them is to use something called LCP, which is the lipidic cubic phase. You don't need to know what that means. Basically, this is the only way to get these receptors to grow is in a membrane. And so what we do is we mix lipids from a membrane together with the protein, and we pray that they form crystals. What does that actually mean to you as the person trying to do an experiment, or if you care and you want to do a micro-ED experiment of your own? We're basically growing crystals in toothpaste. So try and imagine putting this toothpaste onto your TEM grid and trying to get it thin enough to determine a structure. And that's extremely challenging. So the first one we looked at was called the A2A adenosine receptor. This is important for things like Parkinson's disease in your brain and some other issues that can happen in your lungs. Together with the Cherezov lab at USC, we grew crystals that looked like this, very big. And our first attempt at determining this membrane protein structure using micro-ED was, okay, well, we will just pluck the crystals, because we can see them, out of the LCP and put them on TEM grids. This was very challenging, but we accomplished this. We're like, okay, great. We've put this crystal on a TEM grid. That crystal is about 20 microns long and about 5 microns thick. And if you've used TEM for a while, you'll immediately know, big problem. We can't shoot through that, it's too thick. So what we did to tackle this was we took these crystals and loaded them into a dual beam scanning electron microscope with a focused ion beam, where you have an SEM where you can take pictures and a focused ion beam where you can mill things away. And in this way, we are trying to make lemonade given some lemons, or lamelinade. The idea is, if you have your crystal on the left, sitting on your grid like the one we had, you can use the ion beam to etch it into a very thin plate that is perfect for electron diffraction experiments. There's a small example on the bottom, but this is what this actually looks like, where you have your TEM grid here in the SEM, and in the FIB at a grazing incidence, or 52 degrees from your electron beam, you can see all these black dots are actually crystals. And you can watch as I'm milling this in the SEM, you can see as I make a thinner and thinner tiny lamella ready for electron diffraction. We take this milled crystal and lamella, we load it into the TEM, and we can take pictures at multiple scales, where this is the entire grid, and we can CSI and zoom and enhance on different areas here and say, oh, what's that? And you can see our milled crystal and lamella as we keep zooming in on it. And there's our crystal and lamella, where you can actually demarcate the difference between the platinum layer around the crystals, the liquid surrounding the crystals, and the crystal and protein lamella itself here. So from this, our new approach is to use the selected area aperture, as Roberto mentioned, to only use diffraction from this tiny area. And the data we get from this looks something like this. We use phases from molecular replacement in this case to get an all-atom map. So we did this on lysozyme first to make sure it would work, and it worked just fine. We were very happy. So we went back to our adenosine receptor and we tried that focused ion beam there. Looks like it worked beautifully. We were able to just shave this little tiny, this brick-like crystal of the human adenosine receptor down into a tiny little Planck lamella. And we collected diffraction that was very disappointingly to about 12 angstrom resolution, which when it comes to caring about what binds where and what the protein looks like is essentially useless. So we went back and looked at our crystals and said, they looked very dehydrated. It took about 2 minutes to fish the crystal out of that toothpaste and put it on the TEM grid. That's a lot of time and protein work. So we hypothesized that we could do better and we could keep the crystal hydrated by growing those crystals instead of in tiny little drops inside of a glass syringe where you can see this LCP tube here full of crystals surrounded by liquid. We ejected all the extra water out of this, leaving only the LCP behind, and mixed it with something called PEG, which is, it flows and it just acts like a liquid, giving us this beautiful slurry. Put that on the grid and got beautifully hydrated crystals. These crystals look different and they look better. We crossed our fingers, made lamella again, and were able to collect a high-resolution data set of the human adenosine receptor that gave us a map that we were able to build the entire protein structure inside. That mesh being the map and the all atom being ball and stick. A better view would look something like this, where the receptor is floating around and you can see some lovely molecules we identified abutting the receptor. In this adenosine receptor, we identified the antagonist drug called ZMA, bound right down the center of those 7 transmembrane helices. And it was surrounded by 4 cholesterol molecules that facilitated packing between the proteins. And we could kind of visualize how it would pack if it were inside of a membrane, which lets us know how to make new things in the future. So this is kind of where we're at in terms of membrane proteins, which is very exciting. And to give you just a tiny peek into what's important to maybe you guys is all of that I've shown was done on a CMOS detector. And we get asked pretty often, well, what about counting? X-rays use counting detectors where you say 1 X-ray comes in, you say that was 1, rather than an X-ray coming in and causing a cascade of other effects and saying, well, there's some intensity there. So we did this, and using modern electron counting detectors, we were actually able to do something rather amazing, and that was collect a now 0.9 angstrom data set of the protein lysozyme using counted data. And this let us ab initio phase this protein structure. You might not know what that means. Ab initio just means from the beginning. It means there's no bias. So our map, we can generate without knowing anything ahead of time. We can just say, please just give us a map. I want to know where the atoms are. So 0.9 angstrom, what does that mean? So for this protein structure, and you can maybe pick out some intensities here on this counting detector, and they look really good. So they're not capped and they're not counting too fast or too slow or too noisy. So at 0.9 angstrom resolution, one slice through this protein looks like this, where as a structural biologist, I'm playing the game of where are all of my atoms? And those blue blobs are the map. So placing the atoms of where are all my atoms in the map becomes super easy. And at these resolutions, we can actually also see where are all of my hydrogen bonds, which we can identify between, in this case, a tyrosine and an aspartic acid. A really fun thing to teach you all a little bit of biochemistry, maybe by the end of the day, is this protein. If I went through and said all of the amino acids that make this up, all the atoms, what does that look like? And so for every amino acid, you can see I've color-coded the atoms and the ball and stick model you would draw and make. And you can see, we can see where all of the oxygens and carbons and nitrogens and everything is in all of our protein. And we're hoping to push this even further in the future with even faster counting detectors, which I'm sure Anna will talk to you about after me, and hoping to do even more exciting work as we continue to push this forward. So I'd like to thank you for inviting me to come give this talk. I hope I didn't ramble or talk too crazy or fast, and I'm happy to take any questions you guys might have.
Thank you very much. It looks like we have a question in the question and answer section. I can read it and you can probably pull it up as well, but it says, for micro ED, any need to use heavy atoms bound to specific areas?
Nope. I'm not sure if that was directed at whether we need to do isomorphous replacement, which is a method for phasing. So we did not have to. In this case, we could, I mean, you could even, we started from a small fragment of atoms, and we just used something called density modification, where really we started from essentially random phases and then used density modification, and the entire protein popped out in about a minute.
The context might have been that stain is often used in imaging, right? So if you stain, can it also modify diffraction, or would it benefit? Probably that was the context.
So we don't typically stain. So I have done diffraction from stained specimen. The diffraction is typically worse. So for biological work, we vitrify our samples because we want to maintain the liquid-like environment they were in prior to freezing. So everything we do is frozen without any stain, and that usually gives us the highest possible resolution.
All right, well, we have a ton of questions in the question and answer section. Maybe we'll do one more. How are you managing the dose on your direct electron detector in the diffraction mode?
Oh, it's a great question. So there's probably a lot of different approaches to this. What I did when I did this initial work was this was performed on a Titan Krios at 300,000 electron volts accelerating voltage. And it has 3 condensing lenses, which means that the beam is essentially always parallel. What this means is I can use the smallest condensing, so C2 aperture, to lower the dose as small as possible, the largest spot size, and then I spread the beam out to 25 microns across, which is enormous, and then took a very long time. I want to say about it's like 4 or 7 minutes to read out all of the data so that I could get all those individual electron events. And then to make sure that it wasn't drowned out in all of the background you'd get from the 25 microns of beam size, we used a selected area aperture to only get the diffraction right from a tiny 1 to 2 micron area of the protein crystal. So in this way, the electron counting worked without too many problems.
All right, well, thank you very much. There are some more questions in the question and answer section. If anybody else has any questions throughout this next break, please feel free to ask Michael. And thank you so much again for your wonderful talk.